What's up, guys? So we're back, and we're gonna pick back up where we left off. Turn the echo off. We're gonna pick back up where we left off with the end of empirical formula, and I had a couple extra problems for you to do, and so I'm going to show you those right now. And let's just get straight to it. Got 3 topics left to teach on video or virtually here. We've got empirical formulas, mole ratios, or empirical formulas practice, mole ratios, and then full-on stoichiometry. That's it. So we'll try to do these in as few parts as possible. I'm going to remove my background here in a second. Okay, so the first one, these are 3 practices we did in class for the do now. Actually, the first one we did for do now. The next one I kind of urged on for students to try. So you're going to have the same opportunity. Try to do the first one now. If you'd like, you can pause. Otherwise, I'm about to guide you through the process, just to remind you again from the last video. Okay, so here we go. We have up here, step 1, write the percents, 89.94% carbon, 10.06% hydrogen. Then rewrite them as grams. Then we convert the grams into moles, which is a typical practice, a common practice when we're given grams of anything. Convert them to moles. We get 7.495 moles of carbon, 10.06 moles of hydrogen. Then the next step, step 4, and we don't need to round yet. We don't need to round very much. If we can plug in, if the calculator doesn't give us too many numbers, we can write down exactly what it would give us for the number of moles. We don't need to round yet. You round at the very end, actually after this next step. So next step is reduce. That means we look at these 2 numbers, 7.495 and 10.06. And the lower of the 2 is the one that reduces the rest. We divide all of them by the lowest one. So 7.495 is divided by itself, gets it 1C. 10.06 gets 1.342H. But at this step, we're allowed to round. We should actually round that number to the nearest whole, quarter, third, or half. So is 1.34, is that near 0.25, 1.33, 1.5, or 1.75, or 1.67, because that'd be the 2/3 mark? Is it near to which one of those? Answer, 1.33. So we round it to 1.33, which is 1 1/3. Well, we write it in our formula and get C1, H 1.33. Well, you might be saying to yourself, why do we write C1? We don't need to write a 1 subscript, you're right, but we also cannot write a decimal as a subscript. So that's another issue. Well, not an issue, so that's an issue. The first one's just a finicky, a pointed thing. How do you get rid of the decimal then? Well, we can multiply the whole thing by something to get rid of the decimal of 1/3. 3 times 1/3 does that. But if we do it to one thing, just like if you were reducing a fraction, if you try to change one part of the fraction, you must change the other part as well. So if we want to reduce this formula or make it work to a whole numbers, we have to multiply the whole thing by 3. If you calculated it, you get C3H4. Good job. That was just another practice in class. Other 2 problems were the percentages there for P and O, and then number 3 there. I had students practice those. They got out a little bit ahead of me, and then I showed them on the board how to do it. So you do it right now. Pause. I'll prepare my board, and we'll reconvene for that one. All right, I'm going to reconvene with you actually at this step in the process. We have the grams of P written as G, converted to moles, and I've given you the mole values, 1.8174. There's a decimal point there in case you can't see. And then oxygen is converted to moles, 2.72875. I said don't round, so I went as far as the calculator gave me. Because why not? We want to go the extra mile to win this thing. Next step is to reduce. So whichever is lower, we divide by that number. 8174 is the lower one, which gives us 1.5 is the rounds, the oxygen rounds 2. And then this, of course, divided by itself is 1P. So P1O 1.5, but you can't have a decimal, so multiply by 2 to get rid of that half, which means we get final answer P2O P2O3 diphosphorus trioxide. Check. Check yourself. Make sure you get it right. And then, of course, I'll remind you number 3, just in case if you kept playing along too soon. Try number 3, and I will prepare it to show you. Please, of course, pause now and try it. And catch you back up here in case hopefully you paused and tried it. Convert it to moles. Got 2, 3, 1, and 3 moles respectively. The lowest number would be 1. Don't forget the reduce step. Sometimes you forget. Don't forget, it wouldn't have hurt you this time, but it will hurt you other times. Divide by 1, so that makes C2H3O1F3. Final answer. You dig? Okay, good. So we're going to continue along in the slides and get you caught up on our route to catch you up, of course. All right, let's keep going then. Let's go slides. So the answers we got, of course, were, gotta change there, C3H4, P2O3, C2H3OF3. Of course, I went over those already. There's some more practice here. You can pause and try those as well. Shoot me a text just so I know that you're paying attention, and I will show you the key to those as well. Okay, show me your work so that way I can verify it. The work, that's the most important part, is the work. One step further though, what if I told you the molar mass of these 3 compounds? Okay, what would you expect? Okay, molar mass of each of these 3 compounds. This goes back to some of the earlier practice concepts here. Molar mass C3H4 is 40. Next one, P 110, and next one is 100. But what if instead the percentages were given to you with the molar mass? This brings up an interesting point. Turns out that if they give you a molar mass like this, that's called the molecular molar mass, which distinguishes between 2 different types of formulas. You may have seen this on number 1 on the empirical formulas worksheet, is that it says there's a molecular formula and an empirical formula. And in the do now, actually, go back there, I give the definition of empirical and molecular. And then I ask you to use that information to answer questions 1A through E, which is that empirical formulas are all the way reduced. They cannot be reduced any longer. There is lowly reduced. You couldn't reduce them by anything because one of the subscripts is 1 or one of the subscripts is odd compared to the other ones, something like along those that nature. Molecular formula means the formula could reduce, but it's representative of an actual occurring substance in the world, and so it's something that was found. A sample was actually found, and it had this molecular formula, and it could reduce to have this empirical ratio, but it actually occurs at this rate. The formula, the molecular formula, so it could be reduced to that extent. Okay, it would turn out that these molar masses would need to be compared to the molar masses of the molecular formula. Because the molecular formula is going to have an unreduced formula, then the molar mass would be exaggerated, right? If we took each of these formulas, C3H3 or C3H4, and we doubled it, made it C6H8, its molar mass would also double to 80. If we tripled C3H8 and made it C3H4, made it C9H12, its molar mass would triple from 40 to 120. Do you understand? Do you follow that? Therefore, the ratio, the comparison of the molar masses between the molecular provided and the empirical calculated, the same ratio between those two would be the rate we can multiply the subscripts. Let's see what I mean. So notice the molar mass for number 1 provided was 120. The molar mass calculated of the empirical was about 40. 120 compared to 40 is about 3 times. That means the formula that produces the 120 molar mass has 3 times the subscript. So 3 times C3H4. You following? Watch again. P2O3 has an empirical molar mass of 110. If we divide the 219.9, which is very accurate based on some two-digit decimal molar mass values from a different periodic table. We divide that 219.9 divided by the 120 of P2O3 empirical, or excuse me, 110. 220 divided by 110. 220 divided by 110. You get about 2 as the ratio, in which case we would double P2O3. Let's see. So how do they compare? 3 times, 2 times, and 1 time to the empirical molar masses. So we would triple, double, and leave alone the formulas. So that the molecular formulas, which can be reduced, but whose molar masses equal the molar masses provided, that reveals that the formula we calculated was only the empirical. By doing the empirical formula steps, it gives us the empirical formula, but it does not give us, it gives us the foundation for the molecular, but does not give us the molecular until we divide and find out what rate the molecular molar mass compares to the empirical molar mass. So we take the molecular molar mass divided by the empirical molar mass to find the rate that we would change the formula. So 2 differences exist between molecular molar mass and empirical formula, or molecular formula and empirical formula. The subscripts and their molecular masses, or the molar masses. They differ by the exact same rate. So if we can divide one by the other and find that value, the value of difference of comparison, the factor, then we can use that to determine the other component. Usually it's determining, like in this case, the new formulas, the molecular formulas. Isn't that neat? So there's another practice problem you could try on your own. I'm going to coast through it. It's actually the one we did the other day. Oh, it's the one we did the other day, which is a molar mass, empirical molar mass of 88. If the actual molar mass was quantified as 176.3, divide them into each other, and we realize the rate is twice as much. So we would double the formula, the empirical, to get the molecular. Cool. So, had a little quiz grade. We didn't actually do any other. We did that. We actually postponed that quiz because of other things. We had a time crunch. I had to be out one of these days. But anyway, so stoichiometry skills up to this point. Pause and read those, will you? And stoichiometry skills coming soon are mole ratios, full-on stoichiometry, and then a few extensions on those ones listed there with the plus sign. Pause a moment and read those as well. Okay. Then we did some more practice on. Actually, we didn't do any more practice on that. We jumped straight over into balancing equations. So this brings us into. Let's see. We had Thursday was day 1. Monday was day 2. Friday was day 2. Monday was day 3. Tuesday was day 4. Wednesday was day 5. And so we're through the middle of day 5 at this point in time, because on day 5 is when I went into this topic. And today's Thursday, day 6, and we just practiced this and the next topic all the way around. Oh, so Tuesday, day 4, actually, so we're halfway through day 4. I take that back. Okay, so halfway through day 4 means we have to take a look back at balance equations. Remember these? Balance equations represent reactions, and they represent the law of, they demonstrate the law of conservation of matter and mass. Well, remember these equations, balanced. Now, stoichiometry provides us the true and real and meaningful practical reason for why we balance in the first place. Stoichiometry refers to is a relationship, a chemical term referring to the relationship between quantities of products and reactants in a chemical reaction. Thus, when we balance chemical equations, we can actually look at the whole number of values that demonstrate this and come up with a set of ratios. The coefficients are those whole number values. Those whole number values indicate mole ratios that can then be used as conversion factors for converting to any amount of type. All right, I'm not sure when I lost you there, so I'm going to try to go back real quick. Stoichiometry refers to go through balanced equations. Those provide us what's called mole ratios, and stoichiometry leverages that understanding. Sorry, my camera quit out. To relate quantities of reactants to products and products to reactants based on the balanced chemical equation. We use the whole number values within the chemical equation, which is called coefficients. So here's one example reaction, and we would say that because this reaction in the word form takes place, we can write the balanced chemical equation to match that. So obviously, it's an abbreviated version of explaining a reaction, but it also provides us information that's useful. Okay, namely, we see that 1 mole of nitrogen corresponds to the 1 coefficient in front of N2. 3 moles of hydrogen corresponds to 3H2. 2 moles of NH3. Now, this is more than just meets the eye. This allows us to convert between any quantities of products and reactants in that actual equation. Do you see? Are you following me so far? Let me show you what I mean for this. All right, so first thing we see here is that N2 plus 3H2 yields 2 NH3 as the reaction. We saw this kind of demonstrated out already, that 1 mole, we can also put the word mole in there, and that gives us what's called these molar ratios, which means we would say 1 mole N2, because this reaction is taking place, we're saying as 1 mole of N2 is occurring and this reaction is occurring, there is also present 3 moles of H2 because of the reaction. As that is occurring because of the reaction, there's also occurring the product 2 moles of NH3. And this is what's called the mole ratios. They each act like conversion factors as well. So let's just say we have, given this reaction, in a reaction amount, we have 4 moles provided of N2 as a reactant. How many moles of NH3 would be produced given that initial reactant? So we would plug in a T-chart. The given value is 4 moles N2, and we put that in the upper left-hand corner of a T-chart. The wanted value or asked for is number of moles of NH3. We put that in the upper right. Moles NH3. We drag our mole N2 values down. And then we need to find some sort of ratio that relates moles of NH3 to moles of N2. It turns out when this equation's happening, that tells us a ratio. So we would say 1 mole of N2, because there's a 1 next to N2 as a coefficient, relates to, at the same time, equals 2 moles of NH3 given the reaction. We've been able to discern that and fill out our T-chart, and then we multiply from there. Multiply and divide. We do what the T-chart dictates. 4 times 2, divide by 1, cancel units, and we get 8 moles NH3. Voila. Okay. How about some more practice on this one? Okay, we've got some other equations here that says the 16 rubidium plus S8 equation yields 8 Rb2S. And the first question is, if I have 7 moles of S8, that means we put that in the upper left-hand corner of a T-chart. 7 mole S8. And it says how many moles of Rb2S. I see the words how many. It wants moles of Rb2S. That goes in my 2 section. Mole Rb2S. Bring my moles of S8 down. Then I look at a relationship between moles of Rb2S and moles of S8, which would be 8 Rb2S to 1 S8. That's 56 moles of Rb2S. These units would cancel, leaving only the units up top in the upper right. Another one. If I have 3.5 moles of Na, react with Cl2. Okay. It gives me 3.5 moles of Na. It says reacts with Cl2. Is that asking anything about Cl2? No. All it's doing is indicating that Na reacts with Cl2, which means I need to look at this equation. That just doubly affirms that that's the equation I want to look at. It's basically useless information for solving it anyway. To form NaCl, how many moles, well, there's how many again, how many moles of NaCl, that's where we're going to, so that goes in the upper right-hand corner, moles NaCl, and by default it becomes my units, moles NaCl, because I'm going to follow the systematic trend here. Moles NaCl right there. Okay. Then carry my units down, mole of Na. Now I need to look for a relationship between NaCl and Na. In other words, what does the equation say is the number of moles of NaCl that are present? 2. What does the equation say is the number of moles Na is present? 2. Times 2 divided by 2 is just 3.5 moles of the new unit because the old units cancel. Check. Next one, 7.2 moles of Li reacts with aluminum chloride to form lithium chloride. That just means look right here. How many tells me what I need to put in the upper right. Moles LiCl from moles Li. What relationship is present there? 3 to 3. So it's just 7.2 moles Li. Good. Okay. Now this second half, actually, we just barely introduced it on day 4 on Tuesday. Day 5, Wednesday was when we really hammered this topic right here. So we're into day 5, about the first 1/3 of the way, maybe 1/4 or 5th of the way through at this point. But we still have one more question left to answer, so let's do it here together. So get ready. Okay, next part here, number 4, says that 11.7 moles of C, 11.7 moles of C, react with 6.2 moles of SO2. When we have a given, we put it in the upper left-hand corner of a T-chart. So I did it. We have another given. So I need another T-chart. 6.2 moles SO2. Good. Then the question says how many moles of CO, so that needs to go on the converted portion on both T-charts. This time, however, we bring down our units. Mole C, mole SO2. And we look at the relationship between those. Mole CO is 4 to C's 5. And 4 COs to 2 SO2s. And then we do the calculation. We end up with 12.4 mole CO here. And 9.36 mole CO here. So now we have what CO is formed, how many moles of CO is formed. And the question is, wait, both, we're saying one reaction occurs with 2 values added together, of the 2 reactants. Yet 2 different amounts of CO is formed. 2 different amounts of CO. Is that possible? Can we have 2 reactions? Which one of them has got to be correct? Which amount of CO is the actual amount of CO that's formed, which would be called the yield, theoretical yield in this case. How much of those CO would actually be formed theoretically? Well, as it turns out, the amount of CO that would be formed is the 9.36 CO. The lesser amount that is formed, theoretically calculating, is the amount that would be formed in the theoretical yield. Because as soon as 11.7 moles of carbon was spent, in the reaction that required it, 9.36 moles of CO would be made. And as soon as 11.7 was used, turns out it cannot make any more CO. Even if there was enough SO2 to make 12.4 CO, if I only have enough C to make 9.36, then I would run out of C, so that the number of SO2 would not actually be able to make 12.4 in reality, because I'd run out of the C first. C is run out as soon as 9.36 is made. So 6.2 could make 12.4 if I had unlimited C, but I only have 11.7 C. Play that back again if you didn't follow what I'm saying here. As soon as we get 9.36 moles of CO formed, we run out of C, so the reaction has no more C, only SO2 remaining, and the product remaining. We've run out of carbon. We've run out of a reactant. We can't continue. The reaction can't go if we run out of reactant. This is a practical implication, meaning that the element or the reactant that led to the lower amount produced, led to the theoretical yield, the lower yield, the reactant that did that is called the limiting reactant. So because of that, we would say that carbon is labeled the limiting reactant. The analogy I used in class to paint this picture was sandwich making. Let's imagine that you have in your pantry, you take out all of the ingredients you have to make sandwiches. You got loaves of bread and cheese and meat and mayonnaise. Just a simple sandwich, has 2 pieces of bread, 1 piece of turkey, 1 piece of cheese, and a spoonful of mayonnaise. Think about how those are originally, how much comes in each package of each of those things, right? Bread is 10 or 16 to 20 slices, which would give us each. If it takes 2 pieces, it would give us 8 to 10 sandwiches, right? Turkey comes in about probably 20 in a pack, so we'd have 1 slice per each. That would make 20 sandwiches, right? Cheese comes in packs of maybe 14 at the smallest, so that'd be 14 separate sandwiches that it could produce. And then mayonnaise comes, you probably get 60 sandwiches out of probably 60 tablespoons or 60 spoonfuls of mayonnaise in there or more, of a small jar even. So that would make 60 sandwiches. Let's just say 30 sandwiches because we're talking about a real small jar. At that point, we're able to say that which ingredient will we run out of first? Probably the bread. We'd be using 2 at a time. We'd probably get 8 to 10 sandwiches with the bread, and then all of a sudden we'd have this cheese left over, meat left over, and mayonnaise, but we wouldn't have enough bread to put with it. So we'd run out of bread. That makes bread the limiting ingredient. Okay, long story short, that's our limiting ingredient. That's the new concept that's gleaned from this. Now, I want to point out what that brings us to. That brings us into a worksheet here called mole ratios. Take a look at this worksheet. It has you practice more of the same things. Writing the mole ratios. Here is a longhand format of the mole ratios. This is a long-handed format of the mole ratios. Of course, you could also write it in just straight up a way. I could say this one, 4 moles Al equals 3 moles O2 equals 2 moles Al2O3. Okay, and then of course that brings us to some more practice problems. And there's 4 sides to this, but it moves so fast because you're talking about easy T-charts. We're talking about right here, 1 mole Al2O3, 2 moles of Al from moles Al2O3. And then we look at the conversion, or look at the coefficients here. We have 2 next to Al2O3. We have 4 next to Al. Multiply, divide, and you get the mole ratio. That's what we worked on the rest of the way. Finish that worksheet. I do want to make one more note to point out here because I want to stretch you each time we do these videos. I don't want you to be hampered by waiting on me each time. The next iteration is to say, okay, now after this worksheet, after doing the mole ratios worksheet, we have the ability to, from the first worksheets, first 3, convert from grams of substance to moles of the same substance. grams A to moles A. We can convert from, I actually have a great visual aid for this one as well. I'm going to show it to you up on the board. So, just going to watch me scroll really quick, and we're going to all be okay. Okay, so the way I did this in class was I said we know how to convert from grams of a substance to moles of a substance, substance A. And then we also learned simultaneously converting moles of another substance, problem, question number 2, whatever on every the first 3 worksheets. Moles of substance B to grams of substance B. Bottom line, we can go from grams to moles, moles to grams. Those are the first 3 worksheets. Now, after this mole ratio worksheet, you can convert from moles of one substance to moles of another substance as long as you have the balanced chemical equation. So if we put them all together and insert this last scale we learned in the middle, then presumably I could be given a grams amount, convert it to a moles amount of substance A, then using the balanced chemical equation and in this step only, convert from moles of A substance to moles of B another substance, and then carry that value on down from moles B to grams B. I can now convert substances from a practical value quantity in mass to another substance in that same practical quantity of grams. So, interesting leanings on this is that it brings up another worksheet opportunity. This is what it is. This is actually task number 7 as far as I remember it. Yep, task number 7, intro grams to grams conversions. And if you just read the instructions and follow what it says to do from one step to the other, you will be able to finish this worksheet. Send it to me. Of course, I want to tell you one caveat. If you just read it and just do what it says, one step at a time, this is where we're going. This is the ultimate trajectory. This will get you through the end of class on Wednesday. And then some students were able to finish that, had enough time to work on that, finish it, and then work on the next iteration, which is this worksheet, which has you do, which in this case, I don't break it up into steps for you. Sometimes I don't balance the equations. Sometimes I don't even provide the equations. I just give you the words. So you have to go back to balancing equations unit skills and turn words into a balanced chemical equation correctly. Sometimes I don't give you the actual products. You have to predict those, to rearrange and know the reaction type. And then you actually have to work out the balanced chemical equation, balance it, and then convert all of these values using the skills of this. So first, start with this worksheet right here, intro to grams to grams conversions. And if you're really feeling good about it, take these exact 3 steps and apply them to any one of these questions. Number 1 is really easy because it's really easily balanced. Show me in your 3 steps and send me a picture and I can evaluate you. And that's basically where everyone is as of the beginning of class on Thursday, or maybe middle of class on Thursday, is they're in some form or fashion working on this activity. Now, there is actually one other thing that was handed out, mostly because it's a great project grade. It should be an easy one. And also because we had a lot of time on Thursday to work, was we have this assessment project. It's going to be a foldable. That's also a review of all the topics for this unit. Okay, and I handed this out for everybody. I'll attach this as well as a document. And here's a little visual image of the foldable itself. And here's one foldable folded up so that it even looks like the visual image, except for this was version A and this is version C. See, it's got the tabs, it's got the top stuff. And anyway, so those are some things that are on the docket. The rest of the time is work time, work days. I might throw up a demonstration video of me doing some longer form conversions. I just want to get this out there to you, let you have access to it, get to it, send me your questions, send me your work on this, and then we'll go full circle on these. And once again, I'll send a video probably out tomorrow to demonstrate some of these problems with you. And keep up the good work. And once again, let me know take pictures of those worksheets, send me pictures, upload them to some documents, or send me a message, and I'll give you a place to upload it. Thanks for working so hard. Go Dogs, and see you next time.